compiling TclQ to native code. So this is joint work with Kevin Kenny. The background to this is that Carl Lembauer of FlightAware has set some challenges, grand challenges. He wants his challenges were twofold. One, to make TclQ go twice as fast, and the second was to make TclQ go 10 times as fast. Just headline figures. So, going 2 times faster is basically getting into the same territory as Perl. We can probably do that by improving things like our I/O handling and things like that. Maybe a bit more work on the bytecode optimization. But going into 10 times faster, you need a completely different approach. Yeah, there's no way that we can make the existing TclQ implementation go 10 times faster just by incremental changes. So instead, we need to actually go generate native code out of TclQ, which is quite challenging because TclQ is a very dynamic language, and if you're going to generate native code, you have to have types. You absolutely have to have types. There isn't. Because otherwise you just cannot possibly do it without losing a lot of performance. Also, then you also need to support lots of platforms and all sorts of little things like that. I mean, it's just complete headache. So the approach that we're using is actually to generate stuff using LLVM. It solves almost all of the problems for us already, and basically, what we're ending up targeting is almost like going to a somewhat high-level machine code. So that's actually relatively straightforward. There was an existing TclQ package to get us started, but there are some downsides. The number one of which is that any time you have an error, you get a core dump. Which makes debugging really quite a lot harder. So what we do is we take TclQ's bytecode. So we use the existing TclQ bytecode, then we generate from that a new, in effect, what's like a new bytecode. It's what we call it quadcode, and the idea is that this gets rid of all the stack and is much easier for us to analyze. So yes, that's the Steve Landers picture. So we've been doing some analysis, and so we have some TclQ code. That's really easy. We can say that A is in that, and then some bytecode which is equivalent to, and then we do a little bit of optimization, and we get the equivalent quadcode, which just works with named variables and literals. And the big thing is that we've got rid of the stack here, and it's much easier to analyze. It's a more extended example. I won't go through it because we have
an execution engine for the quadcode, an interpreted execution engine for the quadcode.
No, but we could do, but we haven't.
Well, I'm just thinking that
we could.
You're not getting 10x speed performance on that, but you might get some.
This is an interesting question, but we haven't.
Okay.
At the moment, it's actually anything that we did with it would be rather slower, but that's because it's actually all in TclQ. So, instead, what we've got to do some analysis so that we can do static single assignment analysis, do lifetime analysis. So this allows us to actually work out what the lifetime of values really are. We can do type analysis. So another example that I am skipping over for just because it's difficult to read and not very informative. We've done quite a bit of work with deducing what the actual types are in TclQ. Everything is still a string, but that's because string is at the top of the type hierarchy. So all booleans, they're strings still, but it turns out that if we know it's really a boolean, we can use a more efficient internal representation. So So we've also got a whole system for handling failure codes. We can do determined types out of operations. We can do things with introducing type narrowing operations, and then we can actually. And then what happens is, if we can prove that they're useless, we then throw those away. And there's a lot of techniques like that which actually allow us to actually generate much more efficient code. We can actually even do type analysis now across procedures. This is new since the TclQuadcode conference last autumn. So in fact, we can actually take a whole package of procedures and actually compile a whole lot in one go, and then it will actually generate optimal code from that. We've got some neat tech along the way, sort of like, so we can do. So yes, I mean, the TclQuadcode could be an execution target in itself. It's just that we're not using it as such, and we're not putting any design effort into making it as such. But that's not to say it couldn't be. It would be straightforward to do so, I think, because the operations are typically very, very clear. But it is, it's just not a current design goal. The high design goal is what we do with it next. And TclBDD was originally developed for driving all of this. So that was what was. We don't use it anymore, but it was what was we prototyped the compiler in. So now we can generate intermediate representation. It's closest to assembler, and it is really very, very hard work to work with. But most operations actually end up being calls to a library function, which I've already written. So we're using things like discriminated union types for integers, so that we have a 64-bit representation or a 32-bit representation. It switches to the right one according to what the history of where it came from, and it adds a lot of complexity. But the compiler the LLVM optimizer copes with it all very well. There's a whole bunch of tricky bits, but you end up with a bunch of typecasts, and then at the end you end up it inserts the right operations at the end, and it actually works out all right. So yeah, well, I'll skip over that. And then because we've actually managed to make a lot of guarantees of various things, it actually works very well with the LLVM optimizer. So when we actually get reasonable code out of optimizing things. So this was code generated out of a Tcl version of cosine, and it's actually looking very close to how you would write it if you came coming straight out of C. It's actually not much more complicated than that, and that we're really, really happy about. There's other things which we're still working on. We've done some other pieces of neat technology along the way. We've got closures and locally scoped variables and things like this, which is just things which we've implemented to keep ourselves sane. So anyway, the thing this is the one which I really wanted to get to, which is the description of the current state of performance. So for numeric code, we're looking at speedups typically between 10 and 25 times, which is very, very, very nice indeed. The first time I saw those figures, my jaw hit the floor. I thought I'd done something wrong, and that either was actually just returning without actually computing anything. For handling of lists, little things like doing word counting, which is using dictionaries, which we've unified with arrays behind the scenes. For those, we're getting 2 to 2.5 times speed up, which is not too bad. Tcl's code is actually quite good in relation to a lot of the handling of these, so the performance there is like that. We don't get a lot of speed up with string handling. Again, it actually turns out that Tcl is actually very good at strings. Funny that. I'm not so worried about that. We speed up our error path handling quite a lot. though that is actually technically a non-goal because error path handling is something which, well, you shouldn't be ever relying on the performance of your error path. But it turns out it goes a lot faster, because it can actually simplify things a lot. And yeah, that call graph one, that's actually brand new, and that's really, really nice that it's actually able to take what was actually about, I think it's about 10 procedures that call between each other, and it can then, basically we're feeding in a structured description of an expression, and it's using a switch and to decide how it's going to take it apart, and it actually tests a very large fraction of what TclQuadcode can actually do, and it's actually still managing to deliver a 10 times, well, 11 times speed up. I mean, that's very, very nice. So the summary is that numeric code goes much, much faster. Reference management code often goes quite a lot faster. Not always, and error code could be better. And how much performance we're going to get out of this, it depends very much on what the code is. So it's critically dependent on exactly what code people are actually using. So where we're going to go next? The compiler is getting faster, but it is still quite slow. As in, with 40, 50 procedures that we have in our current demonstration suite, it's taking, this laptop, it's taking a little bit under 10 seconds to compile that, which is not fast enough for a just-in-time compiler, but at the moment is fast enough that we would actually be able to use it for an out-of-line compiler. So we may do that, but actually as a first step. So that actually tangles into how do we actually integrate this with Tcl. We've got more parts of Tcl that we've actually got to cover before we let this out. In particular, we need to have access to global variables, because at the moment everything is local, and that has some real issues. We also need to think about dealing with particularly upvar. We're not so worried about up level, because that's just totally impossible. And also it would be nice to have some things to do with handling coroutines, lambdas, methods and things like that, but at the moment we're just not looked at those yet. And then there's some longer term questions about things like how are we going to change Tcl given that we can have this capability, and that's really a question we haven't looked at all yet. But it has given me a relatively pleasant experience with C++, so perhaps we should consider doing at least an official source interface from C++ and between C++ and Tcl. But that's a longer term question. So I would say any questions, but I think you should be also having all the other people up and have them on the hot seat as well.
So how should we manage when you come in front of us? We can put the chairs